All right, so we left off. So we left off talking about confidence intervals, kind of introducing this idea that, if we build a confidence interval around whatever sample statistic we see, and kind of what we'll start out with is thinking about the sample mean, that if we choose that z value that kind of lines up with whatever confidence level we want in the corresponding alpha, we can kind of guarantee with a certain level of confidence, it could be 90, 95, 99, that confidence interval will include that true population. This was kind of the equation that we were using. We're going to take our sample means, we're going to add and subtract what we'll reference as the margin of error, this thing on the right-hand side here. When we add that margin of error, we get the upper bound, and we subtract it with the lower bound. So how we came up with that margin of error was, well, how many standard deviations away we want to go, right? Whatever that z value is, the number of standard deviations away, we'll go 2 standard deviations away, the standard deviation is 5, and we need to go 10 to either side, right? So 2 times whatever that standard deviation is. Now, in practice, we can kind of do the intermediate step, but we know that standard deviation of our sample means is the square root of whatever the population variance is of the data we sampled from divided by our sample size. So that's kind of where we left off, I believe. Let me skip this and we'll come back to this in a second. We worked through this example. We're thinking about hockey pucks. We take, 49 of them, weigh them, find the sample mean. We then wanted a 99% confidence interval. So remember from last class how we figure out what alpha is. 99% confidence interval, alpha would be what? 0.01, right? Alpha was like the percent outside of my confidence interval, but in decimal form. So 1% outside the interval, decimal form 0.01. So we worked through, how we would build this confidence interval. We now have alpha is 0.01. We've got 2 sides of our confidence interval. So alpha is the total area outside the interval. So there's half of it on each side. So we divide alpha by 2. That's the area that we want. If you want to kind of think about the visual here, it's almost like we've got alpha over 2 in each tail. Well, if I know the area in that left tail, or I know that probability I want, I can look that up in the standard normal table. It'll tell me what z value will give me that area. I then know, if I'm looking up these kind of the left area of the tail, I'm always going to find the negative z value. We said we can kind of ignore the sign because it's already built into our confidence interval, right? We're going to go this many standard deviations below to get our lower bound, this many standard deviations above to get our upper bound. So we looked up that z value. Where is it? There we go. Negative 2.58. We just kind of need the absolute value, so just 2.58 here. And from this point, I think my clicker died. So from this point, oh, maybe my computer's mad. There we go. Right, just a matter of plugging everything in, get that lower number down. Right? So once we have this confidence, we can say with 99% confidence, the true population mean weight is somewhere between about 5 and 10 grams. So we'll work through one more example, and then I'll show you how we do some of this stuff in Excel. So let's say we go back to looking at that birth data, and we find that we take 81 births, right? We find a sample gestation or kind of length of pregnancy be 38 weeks. We'll identify the things that were given pretty easily. That we've got different colors, just kind of fading on it. We're given what that sample mean is, so that was pretty easy to identify. We have a sample mean of what? 38 here. My sample size was looking at 81 births, so n is equal to 81. I have to be given, and we said this is kind of a weird example starting out where we don't know the population mean, but we somehow know the population variance. Wednesday will kind of cover what happens in a more practical scenario where we actually only have a sample. But we got to start out here so we understand how to work with these, because only having a sample variance will throw another wrinkle into this, or into this trying to build. So if I look at that equation for my confidence interval, I've got 3 of the 4 things I need. The only thing left I need is that z-value, right? That gives me alpha over 2 in each tail. So here, I've got a 95% confidence interval. What's my alpha? Yeah, it's the percent outside the interval, so 5% in decimal form, so 0.05. Now the equation reminds me, I've got 2 sides of my confidence interval, so I actually need to look up the area I want in that lower left tail and in the upper right tail is actually alpha over 2. All right, so here, alpha over 2, we'll be looking up 0.025. If I just plug my numbers in here, I haven't even found the z-value yet. I'll take 38, it's my sample mean. I'm going to build my confidence interval around this. I'll add my upper bound, subtract to get my lower bound. What we were kind of referring to this was as our margin of error. I don't know what the z-value is yet. But then from here, I can do it 2 ways. One, I can just plug everything into that equation I wrote on the board, right? Or if I remember that all this represents is the standard deviation of my sample means here, I could calculate it ahead of time and then plug it, right? Either way, I should have put the same answer. So our population variance and our sample size are 9 and 8. So the only thing left I have to do is find that z-value in a second. So we go to my table. If I know the area in the tail, I'm working in reverse, right? So rotate this so we can actually read it. So I'm looking up the probability of the area I want in the tail. So I'm trying to match 0.025 to some value here in the middle. So I start looking, oh, it's exactly right here. All right, this one's an easy one because I can find exactly the area I want. Negative 1.96. Okay, so I found that negative 1.96. Let's say I have these potential answers. We said that positive and negative are built in. So instead of negative 1.96, I'm just kind of looking at that absolute value. Now it's going to do that. So if I'm looking at these potential answers, I don't think here I can rule any out. But one thing that we can remember, potentially in the future, rule certain answers out if I was looking at a multiple choice question, is my confidence interval should be centered around whatever that sample statistic I found was, right? So 38 should be smack dab in the middle of whatever the real confidence interval is. So if I'm going through these potential answers, and 38, my sample mean isn't exactly in the middle, I know that that can't be the right answer. I have to rule that out. But it looks like here, I think they all, yeah, 38 looks like it's exactly in the middle of all. Right? So I can't rule anything out here, but potentially some future problems I look at today. Maybe I can. Any questions kind of how anything I did here? Yeah.
I think I just consider how do you get that 1.96?
Yeah, so we knew that our alpha is 0.025. So if we want to guarantee that we're seeing a sample mean such that there's a 95% chance we see a sample mean somewhere in this range, and there's only a 5% chance we see something outside of that range, well, we can look up and figure out what z-score would give me. Right? Total area in those tails is 0.05. Each tail would have half of that. So I know this is the area I want in the tail, 0.025. When I went to that standard normal table, I looked up that probability in the middle of the table, found the corresponding z-score, which was negative 1.96. But really, I mean, we never really actually write it out this way, but we really have 2 z-values we're using. It's just that they're the same value, one's negative, one's positive. So I could write this out in 2 lines, but kind of the shorthand we typically do is kind of this plus minus here. Yeah, so it's kind of like when we were going through that inverse transformation. That's really the reason why, it's not the only reason I showed you that, but you know, that is a useful tool when we start to build confidence, because we're really using that inverse process. Okay. Any other questions on that? Yeah.
So you calculate it, do you use the negative and the positive z-value?
So it's like you're doing 2 equations. Get the upper bound. 9 over 81. So this would give me my upper bound. And I basically just do the exact same thing, but I'm subtracting that margin of error, and that gives me the lower bound of my confidence. So, yeah, I mean, one thing that could be helpful when you're doing this calculator is I would do it instead of just entering all this on one line. I mean, this is the exact same value. So put this into your calculator and figure out what this is, right? I don't know exactly looking at this, but it's going to be roughly 0.65 would be my guess. So really, once I have this value, okay, 38 plus 0.65, that's my upper bound. 38 minus 0.65, that's my lower bound. Yeah, so it might make more sense practically to calculate that margin there. Now I just have one value that I'm adding and subtracting to that sample. But I would, yeah, do it twice. Any other questions? They're good questions. So I'm happy you still have some. Okay. I think what I'm going to do here, and if we have time at the end, I might return to this. So I had a question. This is basically what we did up here on the board. In the slides here, I calculated the intermediate step just to make it a little bit easier as I was entering in my calculator. But you know, either way, we should have the same answer, which is 37.3 to 38.6 about, right? So notice when I have a pretty high sample size, right, n is relatively large, I can actually say, you know, 95% certainty, the true mean is somewhere in this range. I've got a pretty narrow range of values, right? I've got this down to less than 1 week, right? I'm thinking about kind of where that true population mean is. And that really is in large part due to a couple of things. So we'll talk about some things that influence the size of our interval, right? And then I'll show you how to do it, how we will kind of approach this in Excel. So if I go back to the slide I skipped, there we go. I think towards the end of last class, started to ask some prompting questions, but the one I think I asked was, what happens if the sample mean changes? What happens to the size of my confidence interval? You think about like the length of my confidence interval. If the sample mean changes, what happens to the length of mine? Actually doesn't change at all, right? That sample mean will just kind of shift where that confidence interval values are, right? The sample mean doesn't influence at all this margin of error. The only thing that's going to change the size, or like the width of our interval, is if something changes here in how we're calculating this margin of error. So we really only have 3 things that could change: my population variance, my sample size, or this z-value. But how does this z-value change? Well, that changes when we want to say things with different levels of confidence that have different corresponding alphas. Okay. So we'll walk through kind of what these changes would do. Each one of these components would kind of change the width of them. So I've got it in the slide. So what's the first one? I said alpha. So let's say I said larger alpha here, right? So I want to go from 99 to 90% confidence. Well, my alpha there would be going from 0.01 to 0.1. So my alpha is getting larger when I want to say things with lower levels of confidence. Kind of sounds a little bit counterintuitive, but the reason why is because if I want to say something with a lower level of confidence, right, then there's going to be fewer sample means that will have a confidence interval that includes a true population mean. So saying something with a lower level of confidence, the area outside the interval will get larger, right? Alpha will get larger. If alpha gets larger, yeah, use 0.01 over there, but we could use this example where we had 0.05 as alpha. If alpha then goes to 0.1, our alpha is getting larger. I want a greater area in those tails. So what's going to happen to the z-score if I wanted a greater area in those tails? What's going to have to be closer to 0, something smaller, right? Now I don't say less than or greater because notice we're dealing with kind of 2 values and one's negative. So if I start saying greater than less than, a larger negative value is actually less. So I'll just use kind of the terminology. Our z-score is going to get smaller, right? Closer to 0, smaller in absolute value. So if our z-score is getting smaller, guys over there, what's going to happen to our margin of error? Not the confidence interval, what's going to happen to that margin of error? This is my margin of error, and z is getting smaller. What happens to my margin of error? it's also getting smaller, right? If this is the same number, I'm just multiplying it by something that's a smaller value, well, then my margin of error is going to be smaller. So I'm going to be adding and subtracting a smaller value to my sample mean. So if I'm adding and subtracting a smaller value to my sample mean, what's going to happen to the width of my confidence interval? It's going to get narrower, smaller, narrower, not as wide, or however we want to kind of say this. So I want to say things with a lower level of confidence corresponds to this larger alpha value, larger area in the tails. I'm going to have a smaller, or kind of more narrow interval. What if, the next one is the sample size. So if my sample size gets larger, that's what the slide cell on correspondence here. My sample size gets larger, what actually happens to my margin of error now? Right? And we're acting like keeping the level of confidence the same if we saw our sample size get larger. What happens to that margin of error? Smaller, right? Why? Well, if my sample size gets larger, this fraction gets smaller, right? I'm dividing by a larger value. Well, if this value gets smaller, I'm multiplying the same z value by a smaller value. The margin of error is smaller, adding and subtracting a smaller value to my sample mean, my interval is going to get more narrow or smaller here as well. And kind of the intuition behind this one's a little bit important. So remember, this component here represented the standard deviation of my sample means. One thing we talked about when we introduced this idea of the distribution of sample means was, if I can take a greater sample size, that's going to reduce the standard deviation of my sample means. So if I'm reducing the standard deviation of my sample means, we said that was like getting a more peaked distribution. So it was kind of guaranteeing or increasing the probability that I see values that are around wherever that true population mean is. So taking a higher sample size, I'm almost guaranteed that my sample mean that I see is more likely to be close to that population, right? I can narrow down kind of where that is because that distribution is more narrow. So larger sample size would decrease the standard deviation of our sample means, decreases our margin of error, allows us to keep the level of confidence the same, but be able to say with 99% confidence, the true mean is somewhere in this much more narrow range of values, which is a good thing, right? We want to pinpoint down where this true population mean is. The third thing, which we talked about, it's not very interesting, I'll mention why. Population variance gets larger, what happens to my margin of error? Population variance of the variable I'm sampling from gets larger, what happens to my margin of error here? It gets bigger, so I'm adding and subtracting a larger value to that sample mean, so my interval would actually get wider. Now, why I said this isn't interesting, we can't influence the variance of whatever the variable we're sampling from, right? We can maybe take a larger sample, we can say things with different levels of confidence, but we can't influence what the population mean is, right, of that variable we're sampling from. So it's important to know that, but in practice, we don't have any influence over it. So, it's just, it is what it is. Any questions kind of over any one of those three things, or here's something said again or differently? So I think now what we'll do, I had one more example in here. I'll save this if we have time at the end, maybe we'll return to it. If not, it's really the same thing. It would be kind of good practice to kind of go back, make sure that you could solve this one on your own. But really it's the same process as what we've been using. There's no new tricks to it, right? So I think we're going to take kind of go back and forth. And this should be in the in-class data folder. It's called confidence intervals blank. Right? So I put this up there. I've got a bunch of different worksheets in here. We'll kind of focus on one of them today. So the one that says known standard deviation and proportion. Right? So we haven't done the proportion yet, but we were just talking about at the end of last class and then today about examples where we had a sample mean and a known population variance or a known population standard deviation. Okay? So we go up here, kind of what that blank file has. These are weird examples where I had a different data set. Maybe I could somehow tell you what that population variance is, right? You can't calculate this if you don't have the population data. So this is something that would have to be given to you, right? So on that Excel assignment, the one example, it gives you what the population variance is. You don't have to calculate that. Okay? But from our data set, we can calculate something like the sample mean and our sample size. So what variable are we going to be interested in? So I've got a bunch of, I think 100 and some schools here. Notice Ball State's one of them. We've got male, female, and total undergraduate enrollment. Okay. Now, well, let me double check because I did change this to make I think a more interesting example. So let's double check to make sure I don't have to show you how to create this variable. I think I originally had it looking at the size. Oh, I can't open it. Hold on. Exit that so I can take a look to make sure we're working off the same thing. So I use a slightly different example for my one class. It wants to download. Oh. Why is it? There we go. It's freezing on me. Let's see if we can. Oh. Let's try this one more time. Why am I not seeing this thing down? Does anybody have it pulled up in front of you? Yeah. What's this? So if we go to the sheet here, that sheet that I was working off of, what's this column say to you? Column I. Does it match up? Okay, just making sure it matches up. I at one point had like if the enrollment was over 10,000, I just want to make sure that we kind of have it. So I've got three variables, male, female, total undergraduate enrollment. I then created this identifier, which I wouldn't expect you to do something like this, but I used an if statement, all right? So I said, if this female undergraduate enrollment is greater than male, put a 1. If this isn't true, put a 0. So basically, I have this 1, 0 variable that it's a 1 if the college had more female undergraduates than male, 0 if they did. Right? So the variable we're going to kind of first start to focus on is this total undergraduate enrollment variable, right? So we're going to find the sample mean, or the kind of mean of enrollment for this sample of universities. So hopefully at this point, this would be a real easy part, right? We can just use that average function. I select that very first kind of observation, Control Shift, Command Shift on a Mac, hit the down arrow. If I hit enter, it sends me back up to the top. Now I've got my sample mean and I've been given this known population variance. I'll then use that count function, right? We've used this in the past to just give me my sample size. Count the number of observations here that have a value in them for this variable. So go down. Now I've got my sample mean, sample size, and this known population variance. Okay. So I'm actually going to move this up just to make it easier so you guys can kind of follow as I'm going through this. So I don't have to keep scrolling. Okay. So all I'm going to do to build these confidence intervals in Excel is basically use Excel to be a calculator, but then also exploit that norm.s.inv function, right? Part of the process to build these confidence intervals was we had to look up the probability that we wanted in the tail, find the corresponding z-score. Well, Excel can do that for us. So I've got 3 different alphas here, right, corresponding to 3 different levels of confidence. What would the levels of confidence be here? So if I inserted a column and I say, okay, what's the confidence level? This first one would be what? What percent confidence would alpha of 0.1 correspond to? 90, 95, and then 99, right? So I'm going to use that norm.s.inv function, right? And we looked at this kind of, I think using exam scores was the example that we worked through before. Well, all I have to do is tell it the area I want in the tail, and it tells me the z-score that corresponds to that. Well, the area I want in the tail is alpha divided by 2, right? That's the area I wanted in each tail. Now, because we're always looking at kind of high levels of confidence, which corresponds to kind of smaller alpha values, right? Smaller areas in that tail, what's going to be true about the sign of the z-score that this function returns to me. The z-score is going to be, I'm looking at kind of a small area in the tail on that left side of the distribution. Those z-values would be, I think someone said it, negative, right? But we said when we actually get to our confidence interval equation, we just need the number of standard. We don't need it to be positive or negative. So there's two ways we can get around this, right? The first way I think is really easy, is just we want to drop the negative sign. So we'll use the absolute value function in Excel. So all that does is take the absolute value of whatever is within those parentheses. So here we'll just drop the negative sign. We could also think about, if I've got alpha over 2 in my right tail, I know that that z value, the positive z value, right, would give me alpha over 2 in that upper right tail. But when I use that norm to S to I and V, I have to enter in the area to the left. So what I could do is, well, if I know the area to the right is alpha over 2, the area to the left would just be 1 minus that, right? So instead of using this absolute value, which I can do that, but instead of using the absolute value, if I simply took 1 minus alpha over 2, I should get the same answer. So I think it was 1.644 before. Sure enough, we get the same thing. Okay. So two different ways of doing that. Now, I very quickly, instead of having to look up 3 different values in the table, once I have this function entered in, just copy it down. It updates to whatever confidence level I want to make in the row below. And I can do this very quick. I don't even have to find my benchmarks, right? If I really wanted to, I could be like, oh, what if I wanted a, I don't know, 87% confidence interval? Alpha would be 0.13, right? I could actually find that z value very quickly as well, right? So I can do whatever I want here. Well, now that I have the z value, I also have the sample mean. I've got my sample size. I've got my population variance. I can use Excel just to be my calculator, right? Equals, take my sample mean. To get my lower bound, I will subtract whatever that z value was that corresponded to alpha over 2. And then I can multiply it by the standard deviation of my sample means. Now, I could enter that all in one cell, like this equation I have on the board up here. I could put times the square root of the population variance over the sample size, or I can do that in a separate cell. So I actually had this structured to do that, right? So down here, I'm going to calculate what the standard deviation of my sample means is. It's also kind of a good, way to show you, you don't have to, like, even though there's no value in there, that cell reference, as long as I end up putting something here, will then update. So hit enter, right? Looks a little goofy here because it's multiplying by blank, which means it kind of multiplies by 0. So I should just end up with whatever the sample means. But if I put my standard deviation of my sample means down here, which I know is just the square root, so SQRT, we'll go up here. It's the square root of my population variance. I'll move this out of the way, maybe. There we go. Divided by my sample size. I'm just going to hit enter. Now it kind of updates that, and I've got my calculation for my lower bound. Okay. Any questions kind of up to this point? Okay. So if I copy this down, what's going to be a problem? I want to find the lower bound for my next couple intervals, right? But what's going to be a problem if I just simply copy this down to? Yeah, this standard deviation is going to move. That cell reference is going to move. Like, I want my z value to go down. When I want it to, I want to use the new z value on the row below. But all of this stuff is going to change as well. So I'm going to freeze every cell reference except for that number of standard deviations away that I want to go to build that confidence interval or that z value. Okay. So once I freeze these, now when I copy it down, those were kind of staying the same, right? So I've just got 3 lower bounds pretty quickly here. Right? Now, one thing we said earlier was if I want to say something with a higher level of confidence, that corresponds to a smaller alpha value. So to get a smaller alpha value in the tail, I had to look at a larger in absolute value z value, which sure enough, lower levels of alpha, that z value is getting larger. And that z value getting larger should make my confidence interval wider. So my lower bound should be getting lower. And in fact, it is here. Okay. Now to get my upper bound, I think the easiest way to do this, we could type it in again, and it's the exact same thing, except for I'm adding my margin of error instead of subtracting it. So, if I copy this over, I have a problem because, oh yeah, my cell references kind of update. So what I'm going to do, if I double click on this cell so I can see the formula, if I just copy it, hit enter to get out of the cell, and then paste. When I copy paste this way and I don't just drag across the cells, it doesn't update any of the cell references, even the ones that I didn't freeze. So I have literally the exact same thing in my lower and upper bounded cells now, but I know the only real difference is that I want to add instead of subtract that margin of error. Right? So all I did there was copy paste that formula just so I didn't have to type it in again. And then I changed that negative sign to a positive sign, right? So I'm going to add to get my upper bound. Now when I drag this down, my upper bound is getting larger and my lower bound is getting smaller when I say things with a higher level of confidence, right? So it's just expanding kind of that range of possible values. Any questions kind of over anything there? You want to see a cell again or okay with that? All right. Yeah.
Let's just freeze it again.
So on a Mac, it's Command T and F4 on just a PC. Sometimes, like if you have a laptop, mine has a function or an FN key. So sometimes you'll have to hold that and then hit F4 because you've got like different, whatever the FN keys or F keys are used for other things sometimes as well. But yeah, F4 should kind of do on a PC, Command T on a Mac. Any other questions? All right, so we'll leave this here. We're going to go to kind of the next statistic that we're going to talk about, which is the sample proportion, right? So similar to a sample mean, right? I believe last week we looked at that data, and we had that maternal smoking variable, right? Well, that started out as just a 1-0 variable, right? 1 if the mother smoked, 0 if not. Okay? So if we were to kind of add up the number of mothers who smoked in that data set, divided by the total number of mothers, we would have a sample proportion of mothers that smoke, right? If 50 out of 100 that smoke, we have a sample proportion of 0.5. If 20 out of 100 smoke well, we have a sample proportion of 0.2. So we can determine this sample proportion by kind of the number of successes. Now, I wouldn't call a mother smoking while pregnant a success, but it was what we were interested in finding, how many mothers smoke while pregnant. So it's just the number of successes divided by the number of trials. Just kind of think about the number of trials is really just our sample size. Okay? Now, if we go back to when we were talking about the distribution of sample proportions, we said they were centered around whatever that true population proportion is. And we knew the standard deviation, right? We kind of determined the variance of the population proportion was P times rho minus P. So we divide that by our sample size, kind of similar to when we were looking at the sample mean. We took that population variance divided by the sample size. We can find the standard deviation of this sample statistic as well. Just now we're looking at proportion, and it follows slightly different kind of set of rules. But it's really going to be the exact same thing when we go to build a confidence interval for a sample proportion. Well, what are we going to build our confidence interval around now? Well, not our sample mean, we're going to build it around a sample proportion. We're still going to be using that standard normal distribution to find the number of standard deviations the way we want to go, or that Z value, it gives me alpha over 2 in either case. It's just now I'll be multiplying by the standard deviation of my sample proportions. That's the statistic I'm looking at. We have an equation for that, so we can also write this as something like this. Except I've got a problem. Right? When I was looking at a sample mean, I was building the confidence interval for where the true population proportion was, true population mean was, because I wasn't able to observe the population data. For a sample proportion, I'm going to build my confidence interval around that for where that true population proportion is, because I don't have population data. But if I'm looking at this, we know the standard deviation of my sample proportions is based off of whatever that true population proportion is. Well, I can't observe that. That's a problem. So what we're going to do is use the best estimate for what that is, which is whatever our sample proportion is. So I notice we kind of have to use our best estimate. As long as you have a sample size over 30, right? This won't be too far off, it'll be a very close approximation. So really from here, it's going to be like the same steps, same procedure. It's just that you've got slightly different kind of formulas, right? But looking up this z-score, the z-value, same exact thing, right? Yeah, the process really doesn't look a whole lot different. So don't worry about this requirement. It's just saying that, you know, if we have portions that are relatively small or large, we need to make sure that our sample size is sufficient to kind of get us over these particular values, right? So n needs to be high enough so that n times p is greater than 5. I'll never give you examples. I'm kind of tricky with this. Just to be really complete here, I kind of threw it up in the slides. So we've got our confidence interval equation, right? Here, I think I said last on Friday, I really shouldn't be calling the sample mean that margin of error. It's not technically correct. We're really only supposed to call that the margin of error when we're looking at a proportion example, but it just makes it easier to talk about. And it really represents a very similar thing, right? So same kind of idea as before. This thing I'm adding and subtracting to my sample statistic, we're going to reference that as my margin of error. Okay. So let's go through an example. So let's say we've got this survey that was done, and it asked people whether or not they were in favor, of a healthcare coverage that covered pre-existing conditions. Right? So they polled 81 people, 63 of the 81 said they were in favor of this. So here's where it might be a little bit tricky, is how to identify my sample proportion. So 63 out of 81 people were in favor of this. What do you think maybe, how would I find my sample proportion? It's just going to be the number of people who are in favor, or the number of successes, over the number of trials, or the number of people I asked. So just 63 over 81, which I think should simplify down to 7/9. Right? So I've got my sample proportion. Okay. My sample size here is 81. If I want to build a 99% confidence interval, my alpha should be what? Yes, 0.01, right? 1% outside in decimal form, 0.01. Okay. So I know I want to find the z-value that gives me 0.01 over 2, right? Because there's half of that alpha on each side of my confidence interval. So what, 0.005? So I go to my table, I try to find that probability that's closest to 0.005. Let me see. It looks like it's in between these two. Right. So negative 2.57 and negative 2.58. We'll use the larger of the two here, so negative 2.58, but then also kind of remembering that it's already built into my confidence interval equation, that positive negative sign, so just 2.5. Now I've got everything I need. It's just a matter of plugging things into that equation, right? So hopefully we might start realizing we start to see these benchmark values show a lot. Right? We're always kind of looking at that 90, 95, 99% confidence level. So keep running the same z-scores, same level of confidence, the alpha levels are going to be simply the same, which we're always going to have the same corresponding z-score. So we'll see these numbers pop up a lot. But yeah, now I've got everything I need, right? Plug in 2.58, 81, 7/9, 7/9, 7/9. Now it's a matter of doing that into my calculator. And kind of maybe here, once again, maybe it makes sense to calculate your margin of error first, just to make it a little bit easier when you're entering things in your calculators from practice. Makes it a little bit more practical. So, right. Once we identified everything, it's really just a matter of putting all of our values from the numerical. Right? Add to our upper bound, subtract to our lower bound. Right? And you kind of see the usefulness of this, especially with proportions, especially when you start thinking about like political stuff. So here, like if I'm a senator or whoever was trying to pass this bill, I look at this and say, well, man, based off the sample data we from the survey we gave out, with 99% confidence, I can say that the people who are in support of this is somewhere between 0.66 and about 0.9, or 66 to 90% of people are in favor of this. This should, if we pass this act, everyone, a large majority of people should be happy, right? Because the true population proportion of people who are in favor of this is somewhere in this range. So even at worst, right, even at its worst, if this was 0.66 to 0.9, I'm saying with 99% confidence, the true population proportion of people who are in favor of this act is somewhere in this range. Even in the worst case scenario, 66% of people are still going to be in favor of this, right? So you can kind of sort of think about how these confidence intervals might be able to be used in practice. Any questions on this? So, I think because I have the Excel assignment, I'm going to go through how we do this in Excel today. I'm going to end class on that. I've got a few more examples, which we'll start working through on Wednesday, just to get some more practice building these confidence intervals, right? But since we've already done some work in Excel today, I think it also makes sense to now look at how we do the proportions in Excel, because it's very similar, right? So if I looked at a data set like this, and I've got this 1, 0 variable. So anytime we're dealing with a proportion, in practice, when I look at the data, when I look at the variable I'm interested in, it'll be 1, 0, right? So if I find the mean of a 1, 0 variable, so I'm going to use that average function, right? Go over and select this 1, 0 variable that indicates that they have female greater than male enrollment. That average function will basically just be adding up all the ones and zeros, but every time there's a 0, that doesn't change anything. So the numerator, when I'm calculating the mean, will just be adding up all the ones. So it'll find the number of schools that have female enrollment greater than male enrollment, and then it will divide it by the total number of observations. Well, that's essentially what I said what the sample proportion was, right? The number of successes, or the number of ones, divided by n, the total number of observations. So to find a sample proportion, or here I kind of said, it's like a mean proportion, you're just finding the mean of a 1, 0 variable. And it should be somewhere between 0 and 1, right? If every single observation was 1, the average of the kind of mean or sample proportion would just be 1, right? That's not a very interesting example. So usually it's going to be somewhere between 0 and 1, right? 0 would be if no school had more female undergraduates than male undergraduates, right? I'm guessing if we went back far enough, maybe we could find a 0 if we went back and far enough in time. But right, in present day, we know that's probably not going to be the case. Well, hopefully that's not the case. Right? We can then find our sample size, same way as before, using that count function. So go over to this variable, select the entire range of data or all the observations. And now we've got our sample size, our sample proportion. The only thing left we need in that confidence interval equation is what? That z-value, right? Well, if I want to find the z-value that gives me alpha over 2 in the tail, it's the exact same process as what I did for the sample mean. So go over here. I use that norm.s.inv function. I'm going to tell it alpha over 2. Right? What's the other thing that I still need to do? If I look up alpha over 2, if I was to do this by hand in the table, the sign of that z-score is going to be negative, right? So before I showed you, you could do 1 minus alpha over 2, or you could simply take the absolute value to just drop that sign since it's already going to be built into our confidence interval equation. Hit enter. Copy this down to find the z-value I need for my next kind of 2 confidence intervals. I now have everything I need. It's just a matter of using Excel to be a calculator. Okay. Now, once again, I think down here, or no, maybe not. I'll give you another label. So I'm going to drag this up so we can see what I'm doing here a little easier. So the standard deviation of my sample proportions, right? That was that component on the end there, just the square root of the sample portion times 1 minus sample portion over sample size. So I'm going to calculate ahead of time. So square root of my sample proportion times 1 minus my sample proportion, and then divided by my sample size. So instead of doing this all in one cell, I'm just breaking up into parts, right? You don't have to do this. You can type it all right into your lower bound equation. I just think this makes it a little bit easier. Okay. So now I've got that standard deviation of my sample proportions. So the lower bound will be, well, I'm going to build my confidence interval around that sample proportion. I'll subtract my margin of error to get the lower bound. What's part of my margin of error? Well, it's just that z value that gives me alpha over 2 in the tail, multiplied by that standard deviation of my sample proportions. Okay? Same kind of thing as before with sample means. If I copy this down, I'm going to have a problem because to build different confidence intervals, I'm still basing it around that same sample proportion, and the standard deviation of my sample portions hasn't changed, right? The only thing changing at different levels of confidence is how many standard deviations away I need to go, that Z value. So the only thing I want to change when I copy this down is the cell reference that has the Z value. So everything else, I'm going to freeze that cell reference. Okay. Now when I copy this down, I'm still using that same sample proportion, still using the same standard deviation of that sample proportion. The only thing that should be updating is that Z value I need to use, or the number of standard deviations away I need to go. Okay. Any questions on anything there? Can you see a cell again, or why I did something the way I did? Okay. All right, so my upper bound, right, it's the exact same thing. So I could type this all in again, select my cells, or just like I said before, double click on that lower bound equation, copy it, hit enter to get out of the cell, double click here, double click here, paste it. The only thing that needs to change, I now add my margin of error. Okay. Hit enter, copy this down. Now I've got 3 confidence levels, upper and lower bounds. I think a lot quicker than you can kind of see doing this by hand. Right? And it's very precise, right? I don't have to round things to the second decimal in Excel, right? The Z value is out to however many decimals you really want, okay? Now, same kind of idea. When I wanted to say something with a higher level of confidence, my alpha got smaller. So if my alpha got smaller, that meant I had a smaller area of the tail. I need a larger Z value that increased my margin of error. I should have been getting wider intervals. Sure enough, my lower bound was getting lower and my upper bound was getting higher. Okay. Questions? There are a couple more things I mentioned before you can get up and start reading. Okay, so next class, we'll work through some more examples by hand. You should have everything you need now to get that Excel assignment done. So this was kind of like what we did today, problems 2 and 3 by Excel assignment. I will slice these Excel videos together this afternoon and post the lecture, but also post just the Excel work. So it's all kind of easier to kind of find. And I will also be putting up a video that kind of introduces the next topic we're going to talk about. So I'll probably start out Wednesday with some ICLR questions about that. We haven't done those in a while, kind of since the exam. We'll kind of start doing a little bit more of those next couple weeks. So that'll be up on YouTube. I'll expect that you've watched it. We'll start class on Wednesday, so we just kind of get through the next topic a little bit quicker. Okay. Other than that, there's no questions for me. I'll let you guys get out of here, and I'll see you on Wednesday. Try to stay dry out there today.